A time series is a stochastic process observed through time, but one historical path does not automatically reveal its underlying probability law. Our first task is to identify conditions under which that path contains stable information for estimation, inference, and forecasting. We will begin with stationarity, then distinguish it from ergodicity and mixing, three ideas that are related but do very different jobs. Three ideas organize this foundation. Stationarity asks whether key distributions or moments remain stable over time. Ergodicity asks whether averages along one sufficiently long path recover population averages. Mixing describes how dependence between distant blocks fades. The ideas are related but not interchangeable, and each supports a different step in time series reasoning. A process is strictly stationary when shifting every date in any finite collection leaves its joint distribution unchanged. This is a statement about the whole distribution, including all moments and nonlinear dependence that exist. It is strong and usually impossible to verify directly from one finite sample, but it gives a clean definition of probabilistic time invariance. Weak stationarity uses only first and second moments. The expected value of y at time t is a finite constant called mu. Its variance is a finite constant called gamma 0. The covariance between y at time t and y at time t minus k depends on lag k, but not on calendar time. That covariance is called gamma k. The autocorrelation at lag k is gamma k divided by gamma 0. It standardizes linear dependence to lie between -1 and 1. Weak stationarity is the working framework for many linear models, but it does not by itself guarantee a law of large numbers or a central limit theorem. Additional moment and dependence conditions are needed. Strict stationarity does not imply weak stationarity unless the required moments exist. An independent sequence with a common Cauchy distribution is strictly stationary because its joint distributions do not depend on time, yet the Cauchy mean and variance are undefined, so the process cannot satisfy the finite moment conditions of weak stationarity. Weak stationarity need not imply strict stationarity. Imagine independent observations that alternate between a standard normal distribution and a centered uniform distribution with the same variance. The mean, variance, and every non-zero lag covariance stay constant. The marginal distribution nevertheless changes between odd and even dates, so strict stationarity fails. Heavy tails make moment assumptions substantive. A student t distribution with at most 1 degree of freedom lacks a finite mean, and with at most 2 degrees of freedom lacks a finite variance. Pareto and stable distributions can have similar problems. We must check moments rather than infer them from a familiar distribution name or from a finite plot. Time series models are often built from innovations. Independent and identically distributed innovations have a common distribution and are mutually independent, usually with mean 0 and constant variance. This strong benchmark makes calculations easy, but financial shocks can be unpredictable in their mean while still having time-varying conditional variance. A martingale difference sequence, or MDS, requires the conditional expected innovation given all past information to be 0. It rules out predictable conditional means, but permits changing conditional variance. This distinction becomes central in volatility models. An innovation can surprise us in direction, while the likely size of that surprise remains forecastable. White noise has mean 0 constant finite variance and 0 covariance at every non-zero lag. It need not be independent. A 0 mean independent and identically distributed sequence is an MDS and white noise. An MDS with constant unconditional variance is weak white noise. The reverse implications generally fail, so the label white noise should not be read as independence. Ergodicity matters because econometricians usually observe one economy or one market through time, not thousands of independent copies at the same date. An ensemble average uses many independent realizations at a fixed time. A time average uses many dates from one realization. Ergodicity connects the second object which we observe to the first object which defines the population. Stationarity alone does not create that connection. Let one random variable z be drawn once and set y at every date equal to z. The process is strictly and weakly stationary. Its time average always equals the same draw z, however, and does not converge to the population mean of 0. The process never forgets its initial random component. For a covariant stationary process, the variance of the sample mean reflects all autocovariances. Each lag receives a weight determined by how many observation pairs are separated by that lag. If dependence decays slowly, many observations carry overlapping information, and the sample mean can remain noisy even in a long sample. A sufficient condition for mean ergodicity is absolute summability of the autocovariances, or equivalently of the autocorrelations after scaling. In words, the total absolute dependence across all lags must be finite. Then the variance of the sample mean tends to 0, and the sample mean converges in probability to the population mean. A random walk gives the contrasting case. I at time, t equals y at time t, minus 1 plus a new innovation. Its variance grows linearly with t, so it is not covariant stationary. Shocks have permanent effects. Paths drift apart, and a sample average does not stabilize around one fixed population mean in the usual stationary way. Mixing formalizes forgetfulness more strongly than ordinary autocorrelation. We divide the process into a past block and a future block separated by n periods. A mixing coefficient measures the largest remaining dependence between events or functions from those blocks. As n grows, the coefficient tends towards 0 when the distant future becomes asymptotically independent of the past. Mixing implies ergodicity under standard stationarity conditions, but ergodicity does not require mixing. Ergodicity concerns shift invariant events or convergence of long-run averages. Mixing requires a form of asymptotic factorization between distant blocks. Confusing the two can lead us to assume much stronger dependence restrictions than a particular consistency argument actually needs. For a stationary ergodic process with a finite absolute first moment, the law of large numbers makes the sample mean converge to the population mean. A central limit theorem requires more. For an appropriate stationary MDS, or under suitable mixing and moment conditions, the centered sample mean scaled by the square root of sample size approaches a normal distribution. For a short memory linear process, the asymptotic variance of the sample mean is the long-run variance. It equals the sum of autocovariances over all positive and negative lags. Serial correlation therefore changes uncertainty even when the population variance at one date is unchanged. Using an independent data standard error would ignore these cross-time contributions. Let me put alpha mixing in plain terms. Take one event in the past and one event in the distant future. Alpha mixing measures how far the probability that both happen sits from the product of their two separate probabilities, and it tracks the largest such gap over all pairs. If the events were independent, that gap would be 0. Alpha mixing is popular because, with the right decay rate and moment conditions, it supports laws of large numbers and central limit theorems for many nonlinear statistics. 3 further coefficients sharpen the same picture. Beta mixing looks at the average gap between the future's probabilities, conditional on the past, and its ordinary unconditional probabilities. Phi mixing asks for that same gap to close more uniformly. Rho mixing takes a different angle. It uses the largest correlation between any square integrable function of the past and any such function of the distant future, not merely the correlation between two single observations. The common thread is simple. Dependence should fade as the gap in time grows. These conditions form a rough strength hierarchy. Phi mixing implies beta mixing, which implies alpha mixing, while Rho mixing also implies alpha mixing. Converse statements generally fail. In applied work, we seek conditions strong enough for the theorem we need and weak enough for the proposed model. A diagnostic plot cannot directly verify an abstract mixing rate. Let me leave you with one working rule. Keep these three ideas apart in your head. Stationarity is what gives us stable distributions or moments to estimate. Ergodicity is what lets us learn from a single long path instead of many parallel worlds. Mixing is what supplies the decay we need for limiting distributions. None of them guarantees the model is correctly specified, and no finite sample can ever prove them. They are assumptions we take on, and we have to argue for them from theory, design, and diagnostics. I want to start with a result that quietly sits underneath everything else in this chapter, the Wold decomposition. It tells us that any covariance stationary process with finite variance splits into two pieces. One piece is linearly deterministic, meaning it is perfectly predictable from the infinite past. The other is purely non-deterministic, built from current and past innovations, passed through an infinite linear filter. That second piece is where all the action is, and it is why moving average representations turn out to be so fundamental. We say that y at time t equals a deterministic term, v at time t, plus the sum over j from 0 to infinity of theta j times epsilon at time t minus j. The theta coefficients must be square summable, and epsilon is white noise with finite positive variance. This is an exact population representation, not an estimated finite model. The deterministic component need not be a fixed textbook trend. It can include a random constant or stationary harmonic components that are perfectly linearly predictable from the infinite past. A random constant reminds us that covariance stationarity does not ensure ergodicity. Its time average converges to that random constant, rather than necessarily to an unconditional population mean. The innovation epsilon at time t is the one step ahead linear forecast error. Start with the best linear projection of current y on all past y values. Subtract that projection from current y. What remains is orthogonal to the linear past and represents genuinely new information for linear prediction. For a Gaussian process, the best linear projection equals the full conditional expectation, so the innovation is also the optimal mean squared forecast error using the past. Outside the Gaussian case, linear projection and conditional expectation can differ. Wold's theorem is fundamentally a second moment result and does not claim that all nonlinear predictability has disappeared. The scale of innovations and coefficients is not unique unless we normalize it. Multiplying every innovation by a constant and dividing every filter coefficient by the same constant leaves y unchanged. A common convention sets the innovation variance to 1 and places the scale in the theta coefficients, or sets theta 0 to 1 and retains an innovation variance. When the deterministic component is 0, the process is purely non-deterministic and is called a linear process. Stable causal autoregressive moving average models belong to this class. Their infinite moving average coefficients typically decay geometrically. Wold's class is broader because square summability permits many patterns that no low-order ARMA model captures exactly. The theorem therefore motivates ARMA models as parsimonious approximations, not as a statement that every stationary series has a finite ARMA order. A finite model is useful when a small number of parameters captures the dominant filter shape. Residual diagnostics and forecasting performance must assess whether that approximation is adequate. Let me make memory concrete. Suppose the Wold coefficient at lag j shrinks like j raised to a negative power, and call that power gamma. For the process to have finite variance, gamma must be larger than 1/2. Now, here is the interesting range. When gamma sits above 1/2, but is no greater than 1, the variance is still finite. Yet the autocovariances die out so slowly that their absolute values do not add up to a finite total. That slow decay is exactly what we will call long memory. That case is called long memory. Distant observations retain dependence that fades at a power rate rather than a geometric rate. When gamma is greater than 1, the filter, coefficients and autocovariances are short memory under the stated conditions. The threshold shows that finite variance and short-range dependence are distinct requirements. A stationary AR1 process provides the standard short memory example. Y at time t equals phi times y at time t minus 1 plus epsilon at time t, with the absolute value of phi below 1. Repeated substitution gives y as the sum of phi raised to j times epsilon at time t minus j. Because those coefficients decay geometrically, a finite MA approximation can be accurate. In an R demonstration, we simulate an AR1 series and fit an MA model with 10 lags. The fitted path can track the original closely, although truncation remains an approximation and the fitted coefficients need not equal the first 10 theoretical Wold coefficients exactly. For a linear process with coefficient delta j and innovation variance sigma squared, the autocovariance at non-negative lag k equals sigma squared times the sum over j of delta j times delta j plus k. The expression pairs every shock appearing in both current and lagged y. Serially uncorrelated innovations are sufficient for this second-order result. If the delta coefficients are absolutely summable, the autocovariances are also absolutely summable. The long-run variance then equals sigma squared times the square of the sum of all delta coefficients. A filter whose coefficients reinforce one another near frequency 0 produces a larger long-run variance and greater uncertainty for long-horizon averages. In frequency language, the long-run variance equals 2 pi times the spectral density at frequency 0. Frequency 0 corresponds to very slow movement. This interpretation links persistence, low-frequency power, and the sampling uncertainty of averages. It becomes especially useful when comparing short memory and long memory processes. Higher moments require stronger assumptions than autocovariances. With independent and identically distributed shocks and a finite fourth moment, we can express the skewness and excess kurtosis of a linear process using powers of the filter coefficients. Mere white noise is not enough because uncorrelated shocks can still have nonlinear dependence across time. Linear filtering generally attenuates the magnitude of standardized skewness and excess kurtosis under those conditions. The sign of skewness can change when positive and negative cubic coefficient contributions offset one another. If innovations are Gaussian, Every linear combination is Gaussian, so skewness and excess kurtosis remain zero. This attenuation does not mean a linear process must look nearly Gaussian in a finite sample. A filter may be dominated by one coefficient. Innovations may be heavy-tailed, or required moments may not exist. Before interpreting sample skewness or kurtosis, check the assumptions that make the population quantities meaningful. The boundary between linear and non-linear processes is subtle. The class of linear processes is not closed under all relevant limits, so a sequence of linear processes can converge to a nonlinear process. Consequently, no universal test can perfectly separate every linear process from every nonlinear alternative, even with an arbitrarily large sample. The right applied question is therefore not whether nature is exactly linear in every respect. We ask whether a linear representation captures the dependence relevant to our purpose. A model adequate for forecasting the conditional mean may still miss conditional variance dynamics, tail dependence, or non-linear responses to positive and negative shocks. Wold's theorem is a representation result, not a ready-made estimation algorithm. We observe neither the infinite past nor the population projection. In practice, we choose a finite model, estimate its parameters, examine residual innovations, and test its forecasting usefulness. The decomposition tells us what a broad, stationary linear target looks like and why innovations matter. Let me pull this together. The picture to carry forward is that stationary dynamics are just the working out of new shocks over time, plus whatever perfectly predictable part happens to be present. The filter coefficients are what set the memory, the autocovariances, the long-run variance, and even some of the higher moments. That is exactly why, in the lessons ahead, we will lean on finite autoregressive and moving average polynomials as interpretable approximations, always judged against the job we actually need them to do. An autoregressive moving average model combines dependence on past observations with dependence on current and past shocks. We call it an ARMA model of order P and Q. The autoregressive order P counts lags of Y, while the moving average order Q counts lagged innovations. This combination can represent rich, short memory dynamics with relatively few parameters. The probabilistic foundations from earlier lessons remain essential. Stationarity makes moments stable. Ergodicity allows one long path to identify those moments, and suitable dependence conditions support large sample inference. Wold's theorem motivates the model as a finite polynomial approximation to an infinite moving average filter. Begin with an autoregressive model of order 1. Y at time t equals c plus phi times y at time t minus 1 plus epsilon at time t. When the absolute value of phi is below 1, the causal stationary mean equals c, divided by the quantity 1 minus phi, and shocks have geometrically declining effects. A positive phi produces persistent movement that returns monotonically toward the mean. A negative phi produces an alternating response around the mean. As the absolute value approaches 1, decay becomes slow and finite samples can resemble non-stationary behavior. At exactly 1, the usual model becomes a random walk with a unit root. The innovation epsilon is white noise, with mean 0, constant finite variance, and 0 autocovariance at non-zero lags. White noise does not necessarily mean independent or Gaussian, and that distinction matters in applications. Stronger distributional assumptions become important for exact likelihood calculations, higher moments, or nonlinear functions of the shocks. An autoregressive model of order P includes the previous P observations. Its stability is governed by the roots of its autoregressive polynomial, We write 1 minus phi 1 times z, continuing through minus phi p times z raised to p. A causal stationary solution requires every root of this polynomial to lie outside the unit circle. A moving average model of order q writes y as its mean, plus the current innovation and q lagged innovations. It is covariant stationary for any finite coefficients when innovations have constant finite variance. Its autocorrelation becomes exactly zero beyond lag q because observations farther apart share no common shock. Stationarity and invertibility answer different questions. A finite MA model is stationary without restricting its coefficients, but its parameterization may be non-unique. Invertibility places roots of the moving average polynomial outside the unit circle, so current shocks can be recovered as a convergent function of current and past observations. For a concrete MA2 process, let y equal the current shock plus 0.5 times the first lagged shock minus 0.3 times the second lagged shock. A simulation should show short clusters of dependence rather than persistent smooth decay. Sampling noise prevents the theoretical cutoff from appearing perfectly in every empirical plot. The lag operator provides compact notation. Applying L to y at time t gives y at time t minus 1. Applying L raised to p gives y at time t minus p. A polynomial in L represents a weighted collection of lags, and the same algebra can describe both autoregressive and moving average sides. The ARP model becomes phi of L times y at time t equals c plus epsilon at time t. The polynomial phi I of L is 1 minus phi 1L, continuing through minus phi pl raised to p. The moving average side uses a theta polynomial acting on epsilon. Lag polynomials can be added and multiplied like ordinary polynomials, while remembering that they act on sequences. Under appropriate root and convergence conditions, they can also be inverted. Inversion lets us express a finite autoregression as an infinite moving average, and an invertible finite moving average as an infinite autoregression. For AR1, the inverse of 1 minus phi L is the infinite sum of phi raised to j times L raised to j. Multiplying the polynomial by this series cancels every non-constant lag term. The coefficients decay only when the absolute value of phi is below 1, matching the root outside the unit circle condition. That cancellation is only formal until we show the infinite sum really converges. So we apply the filter one term at a time and watch the partial sums. What we need is for those partial sums to settle down, getting arbitrarily close to each other as we add more terms, measured in mean square. When they do, they approach a single well-defined stationary limit. Skip that check, and a symbolic inverse can quietly describe an unstable or non-causal solution that does not actually exist. Higher-order polynomials can be factored into first-order pieces. A quadratic autoregressive polynomial may be written as 1 minus lambda 1L times 1 minus lambda 2L. When both lambda values have absolute value below 1, each factor has a convergent geometric inverse, and multiplying the two inverses yields the full infinite filter. The characteristic roots are the reciprocals of those lambda values. Roots outside the unit circle correspond to lambda values inside it. A root on the unit circle creates a unit root or seasonal unit root. A root inside the unit circle prevents the usual forward causal covariant stationary solution and can generate explosive recursion. This root convention often causes mistakes because some software or texts report reciprocal roots. Always check which polynomial is being solved. The economically relevant question is whether the impulse response coefficients in the causal representation decay, not whether a displayed number happens to be labelled a root. Under the relevant conditions, autoregressive and moving average forms are dual. A stable AR model has an infinite MA representation in past shocks. An invertible MA model has an infinite AR representation in past observations. The duality helps with forecasting, identification, likelihood evaluation, and interpretation of shock persistence. The general ARMA model of order P and Q says that Y equals a constant, P lagged Y terms, the current innovation, and Q lagged innovations. The AR side represents persistent feedback. The MA side captures a finite pattern in how recent surprises affect the current outcome. For example, an ARMA11 process may use an autoregressive coefficient of 0.6 and a moving average coefficient of 0.7. Simulated observations display persistent propagation combined with a strong short-run response to the previous shock. The time plot alone rarely reveals the two orders reliably. Different specifications can fit almost the same finite sample. Common factors on the AR and MA sides can even cancel, creating a redundant parameterization. We therefore impose no common roots, stationarity, causality, invertibility, and a normalization of the current shock coefficient before treating an ARMA representation as unique. The common mistake is to choose P and Q from appearance alone. A time plot is only a first diagnostic. Autocorrelation, partial autocorrelation, likelihood, information criteria, residual whiteness, and forecasting performance provide complementary evidence. Parsimony means using the smallest model that captures the relevant dependence, not simply choosing the lowest order regardless of fit. This lesson has supplied the model language. Autoregressive roots govern causal stability. Moving average roots govern invertibility. Lag polynomials connect finite and infinite representations. Next, we study the autocorrelation structures that these models imply and learn how those patterns guide, but do not determine, model identification. So far, our models have lived on paper. Now I want to connect them to something we can actually see in data, the autocorrelation. For a stationary series, the autocovariance at lag k measures how today's value moves linearly with the value k periods earlier. Divide that by the variance and we get the autocorrelation at lag k. Plot those correlations against the lag and we have the autocorrelation function, which everyone writes as ACF. This picture is our first bridge from theory to a real series. Because the process is stationary, the autocovariance depends on separation, not on the calendar date. It is also symmetric. The covariance at lag minus k equals the covariance at lag k. Autocorrelation is standardized between -1 and 1, but a value near 0 rules out only linear association at that lag, not every form of dependence. Consider a stable autoregressive model of order 1. Its innovation variance is sigma squared, and its autoregressive coefficient is phi. The unconditional variance equals sigma squared divided by the quantity 1 minus phi squared. Its autocorrelation at lag k equals phi raised to k, so the ACF declines geometrically rather than ending abruptly. The sign of phi shapes that decline. A positive coefficient gives correlations with the same sign and a smooth decay. A negative coefficient makes the signs alternate as the magnitude shrinks. When the absolute value of HI is close to 1, the decay is slow, and a finite sample may look almost non-stationary, even though the population model is stable. Higher-order autoregressions obey the Yule-Walker equations. For an autoregressive model of order 2, each autocovariance beyond the first few lags is a weighted combination of the previous two autocovariances. The weights are the two autoregressive coefficients. This recursion links an observable second moment pattern directly to the model parameters. For an autoregressive model of order P, the first P Yule-Walker equations form a linear system. The coefficient matrix is built from autocovariances, and the unknown vector contains the P autoregressive coefficients. Replacing population autocovariances with sample estimates gives the Yule-Walker estimator, provided the sample system is sufficiently well behaved. Moving average models leave a different signature. In a moving average model of order 1, current y contains the current innovation and theta times the previous innovation. Its lag, one autocorrelation equals theta divided by the quantity 1 plus theta squared. At lags 2 and beyond, observations share no innovation, so the population autocorrelation is exactly 0. For a moving average model of order 2, the first two autocorrelations may be non-zero, but every population autocorrelation after lag 2 is 0. More generally, the ACF of a moving average model of order Q cuts off after Q. Sample correlations do not become exactly 0 because estimation noise remains. The partial autocorrelation function, or PACF, asks a more selective question. At lag k, it measures the linear association between current y and y from k periods earlier after removing the linear effects of the intervening lags. It is the last coefficient in the linear projection using lags 1 through k. For a true autoregressive model of order P, the population PACF cuts off after lag P. The ACF usually tails off. For a moving average model of order Q, the ACF cuts off after Q, while the PACF usually tails off. These contrasting patterns are useful first clues about model order. An autoregressive moving average model usually has no clean cutoff in either function. Both the ACF and PACF tend to decay. Different combinations of autoregressive and moving average orders can produce very similar shapes, so no visual rule can identify a general ARMA order with certainty. Finite sample plots require restraint. Even when a population correlation is 0, its sample estimate is a continuous random quantity and will almost never equal 0 exactly. Approximate bands around 0 can flag unusually large sample correlations, but their accuracy depends on the fitted model, the sample size, and the assumptions used. A common rough band uses 2 divided by the square root of sample size. This is a diagnostic heuristic, not a universal hypothesis test. Looking across many lags also creates a multiple comparison problem. We should combine ACF and PACF evidence with information criteria, likelihood, residual checks, and forecasting performance. Stationarity, causality, and invertibility describe different properties. A finite moving average process is covariance stationary whenever its innovations have finite constant variance. An autoregressive, or ARMA model, needs restrictions on its autoregressive polynomial. Causality then asks whether current y can be written using only current and past innovations. For a stable autoregressive model of order 1, repeated substitution produces an infinite moving average. The coefficient on the shock from j periods ago is phi raised to j. When the absolute value of phi is below 1, these coefficients decay and are absolutely summable, so the influence of a distant shock eventually disappears. More generally, an ARMA process is causal if y can be expressed as an infinite sum of current and past innovations with absolutely summable coefficients. This condition rules out dependence on future shocks and delivers the operational representation used for forecasting. Autoregressive routes outside the unit circle give causality under the standard convention. Invertibility reverses the direction of the filter. It requires the current innovation to be expressible as a convergent sum of current and past observations. Moving average routes outside the unit circle deliver this property. Invertibility is not needed for stationarity, but it makes the innovation sequence recoverable and the parameterization identifiable. The moving average model of order 1 shows why identification matters. Replacing theta by its reciprocal and changing the innovation variance can preserve every autocovariance. For example, theta equal to 5 with variance 1 has the same second-order behavior as theta equal to 1/5 with variance 25. With Gaussian shocks, those two moving average representations also generate the same finite dimensional distributions. The invertibility restriction selects the version whose coefficient lies inside the unit circle under this parameterization. We also normalize the current shock coefficient and exclude common autoregressive and moving average routes to avoid redundant descriptions. Time series and structural models answer different questions. A time series model summarizes temporal dependence and supports forecasting. A structural model seeks causal mechanisms using economic theory and credible identifying assumptions. A regression does not become structural merely because one variable appears on the right-hand side, and an ARMA fit alone does not establish causality. The two perspectives can coexist. Suppose y equals beta 0 plus beta 1 times x plus a white noise error, while x is a moving average of its current shock and one lagged shock. Under the stated independence assumptions, y inherits autocovariance at lag 1 and 0 autocovariance at longer lags. Thus, the structural relation can imply a familiar moving average pattern for the observed outcome. The regression coefficient describes the proposed economic mechanism only if its identifying assumptions are credible. The moving average description summarizes the resulting second-order dynamics. Confusing those roles can turn a forecasting relation into an unjustified causal claim. Yule-Walker estimation offers a concrete closing example. For a simulated autoregressive model of order 2, we estimate autocovariances at lags 0, 1 and 2, place them in a 2x2 linear system and solve for the two coefficients. In R, the standard Yule-Walker routine performs this calculation directly. The estimates should be close to the generating coefficients in a sufficiently informative simulation, but not identical. Sampling variation, near instability, outliers, and wrong order choice can all matter. Correlation patterns and Yule-Walker equations are powerful because they connect theory to data, yet they remain model-dependent summaries rather than automatic proof of a specification. Likelihood asks which parameter values make the observed sample most plausible under a specified probability model. We hold the data fixed and view their joint density as a function of the unknown parameters. The maximum likelihood estimator, or MLE, chooses the parameter vector that gives the largest value of this function. We usually work with the log likelihood. Taking a logarithm turns a product of many density contributions into a sum, reduces numerical underflow, and leaves the maximizing parameter unchanged. Sums also connect naturally to laws of large numbers and central limit theorems, which makes the log likelihood convenient for large sample analysis. A familiar independent normal sample illustrates the method. If observations share mean mu and variance sigma squared, maximizing the normal likelihood gives the sample mean as the estimate of mu. The variance estimate is the average squared deviation from that sample mean, using sample size rather than sample size minus 1 in the denominator. The maximum likelihood estimate of the normal mean is unbiased and consistent. The maximum likelihood estimate of the variance is biased downward in a finite sample because the mean was estimated, but the bias vanishes as sample size grows. This example reminds us that maximum likelihood does not guarantee exact finite sample unbiasedness. For an autoregressive moving average model, observations are dependent, so the likelihood does not factor into independent marginal densities. Under independent Gaussian innovations, however, we can build a conditional likelihood from the one-step prediction errors. The parameter vector contains the constant autoregressive coefficients, moving average coefficients, and innovation variance. Given trial parameters and initial values, residuals are computed recursively. At each date, subtract the constant, the fitted autoregressive terms, and the fitted lagged innovation terms from observed phase. The resulting residual is the innovation implied by that parameter choice. The recursion makes moving average estimation non-linear, even though the displayed model looks linear. The conditional Gaussian log likelihood rewards parameter values that make squared recursive residuals small, while accounting for the innovation variance. It is evaluated conditional on pre-sample observations and innovations. Unobserved innovations are commonly initialized at 0, and observations may be initialized at their unconditional mean when that mean exists. For a stable invertible process, the influence of reasonable initial values usually fades as the sample grows. In a short sample or a highly persistent model, initialization can still matter. Exact likelihood methods integrate over or model the initial distribution more carefully, while conditional likelihood offers a practical and often asymptotically equivalent route. There is generally no closed-form solution for all ARMA parameters. Numerical optimization searches the admissible region for a maximum. Software may use gradient methods and transformations that enforce stationarity or invertibility. Different starting values can lead to different numerical outcomes, so convergence messages and parameter restrictions deserve careful inspection. The largest likelihood is not automatically the best model. Adding parameters usually improves in sample fit, even when they capture noise. Model selection therefore balances fit against complexity. We compare candidate models estimated on the same observations with compatible likelihood definitions, because otherwise their likelihood values and penalties are not meaningfully comparable. The RK-EE-Chi information criterion, or AIC, equals minus twice the maximized log likelihood plus twice the number of estimated parameters. Lower values are preferred. Its penalty is designed around predictive information loss, so AIC can favor a richer model when additional parameters improve expected out-of-sample approximation. The Bayesian information criterion, or BIC, equals minus twice the maximized log likelihood plus the number of parameters times the natural logarithm of sample size. Lower is again better. Because its penalty grows with sample size, BIC usually favors simpler models than AIC in a moderately large sample. Under suitable assumptions and a finite candidate set containing the true model, BIC is consistent for selecting that model. AIC instead targets predictive efficiency and need not select the smallest true order with probability approaching 1. Neither guarantee applies automatically under misspecification, structural change, or an unbounded search over models. Parsimony means choosing the simplest model that captures the relevant dynamic structure. It does not mean always choosing order 0 or ignoring a substantial likelihood improvement. Too many parameters inflate estimation variance and can create unstable forecasts. Too few parameters leave serial dependence in residuals and distort uncertainty or prediction. A practical order search begins with a defensible maximum autoregressive and moving average order. We estimate each admissible candidate, record its AIC and BIC, and inspect the top contenders. We then check whether fitted routes satisfy the intended restrictions and whether the optimizer has actually found a credible maximum. In the chapter simulation, data are generated from an ARMA model of order 1 and 1. Candidate orders are compared using likelihood and information criteria. A good procedure often ranks the generating order highly, but one random sample can select a neighboring model because the criteria themselves are random. Residual diagnostics provide evidence that an information criterion cannot. Standardized residuals should have no important remaining autocorrelation if the conditional mean is adequately specified. Squared residuals can reveal conditional variance dynamics. Extreme residuals, non-normality, or changing variance may expose weaknesses in a Gaussian likelihood even when its numerical value is high. A common error is to choose an order from one AC F-plot and stop. Another is to compare criteria calculated after different transformations, missing value deletions, or likelihood conventions. A third is to search a huge model grid and report the winner without checking stability, invertibility, residuals, or out-of-sample behavior. Parameter counting also needs care. The total can include a constant or mean, every autoregressive and moving average coefficient, and the innovation variance. Some software reports likelihoods with different constants or effective sample sizes. We should understand the implementation before treating small differences in AIC or BIC as decisive. Gaussian maximum likelihood relies on a distributional specification as well as a conditional mean model. If innovations are not Gaussian, the same objective may still serve as a quasi-likelihood estimator under additional conditions. Standard errors may then need robust treatment. A good fit to second moments does not establish correct tail probabilities or density forecasts. Likelihood surfaces can also be hard to navigate. A nearly cancelling autoregressive and moving average route may create a flat ridge, and estimates near a boundary can make curvature-based standard errors unreliable. Trying several sensible starting values and examining the fitted routes helps distinguish a genuine empirical feature from a fragile numerical solution. Forecast comparison offers a purpose-driven final check. Estimate candidate models on a training sample, produce forecasts without using future data, and evaluate them on a held-out or rolling window. A slightly higher in-sample criterion may be acceptable if it delivers more stable parameters, clearer interpretation, or better relevant forecasts. Order selection uncertainty should remain visible in the final interpretation. When several models have nearly equal criteria, choosing one as unquestionably correct overstates the evidence. We can compare their forecasts, report sensitivity across plausible orders, or average predictions. Small criterion differences often matter less than a common failure shared by every candidate model. If you take one thing from this lesson, let it be the habit of disciplined comparison. Likelihood turns a probabilistic model into something we can maximize. Information criteria charge us for improvements we only bought with extra parameters, And diagnostics and forecasting ask the harder question of whether the fitted dynamics are actually useful. No single number does that job on its own, so keep checking assumptions, convergence, residuals, and how sensitive the answer is to the sample you chose. Forecasting turns an estimated dynamic model into a statement about future uncertainty. For an autoregressive moving average model, the central question is what we know at the forecast origin. We condition on observed values and inferred past innovations, then take conditional expectations of future outcomes under the fitted model. First, identify the unconditional mean. In a stable ARMA model with constant C, the mean equals C, divided by the quantity 1 minus the sum of the autoregressive coefficients, provided that denominator is non-zero. Subtracting this mean gives a centered process and makes the forecasting recursion easier to interpret. The optimal forecast under squared error loss is the conditional expected future value given the information available now. This statement is about the assumed model and information set. A forecast can be optimal within a misspecified model, yet systematically poor in reality, so evaluation remains part of the forecasting problem. For a one-step forecast, every lagged observation is already known. Past innovations are replaced by estimated residuals from the fitted model. The future innovation has conditional mean 0 and is therefore omitted from the point forecast. What remains is the model's predictable component at the next date. The one-step forecast error is the new innovation when parameters and the past state are known exactly. Its conditional variance is then the innovation variance. In practice, parameters and past innovations are estimated, so actual forecast uncertainty can be larger than this clean population expression suggests. Multi-step forecasts are computed recursively. Whenever a needed future y has not yet been observed, replace it by its forecast from an earlier step. Whenever a future innovation appears, replace it by 0 in the conditional mean. Repeating these rules carries the current information through the autoregressive and moving average dynamics. The moving average terms disappear from the point forecast after their finite horizon has passed. In a model of moving average order Q, no currently known residual enters forecasts beyond Q steps. The autoregressive part can continue to propagate the current state, although stability makes that contribution decay over long horizons. For a stable model, long horizon point forecasts converge to the unconditional mean. This is mean reversion in the forecast, not a promise that the realized path will move smoothly. New innovations arrive after the forecast origin, and their accumulated effects cause actual future observations to fluctuate around the projected mean. An ARMA model of order 1 and 1 makes the recursion transparent. Suppose the autoregressive coefficient is 0.5 and the moving average coefficient is 0.3. The one-step forecast uses the latest centered observation and latest estimated innovation. At later horizons, only the autoregressive propagation remains. With an autoregressive coefficient of 0.5, the predictable deviation from the mean halves roughly with each additional horizon after the moving average contribution has passed. A 20-step forecast is therefore very close to the unconditional mean. If the coefficient were nearer 1, convergence would be much slower. Forecast intervals behave differently from point forecasts. At one step, uncertainty reflects one new innovation. At 2 steps, the first and second future innovations can both affect the outcome. As the horizon increases, more unknown shocks accumulate, so interval width usually grows before approaching the unconditional uncertainty of a stationary process. The infinite moving average representation gives a precise interpretation. Right-centered y as current and past innovations weighted by impulse response coefficients. The H-step forecast error contains the future innovations from the next date through horizon H. Each is weighted by the response appropriate to how long it has had to propagate, with uncorrelated innovations of variance sigma squared. The H-step forecast error variance equals sigma squared times the sum of squared impulse response coefficients from 0 through H minus 1. Every additional horizon adds a non-negative term. The variance therefore cannot decrease in the correctly specified population model with known parameters. For a stable short memory process, the squared response coefficients are summable. Forecast error variance then approaches the unconditional variance as the horizon becomes large. This plateau reflects lost information. Sufficiently far ahead, the current history contributes almost nothing, and the forecast is essentially the unconditional mean with unconditional uncertainty. The forecast interval also requires a distributional choice. Under Gaussian innovations and known parameters, we can combine the point forecast with the forecast error, standard deviation, and normal quantiles. With heavy tails or conditional heteroskedasticity, a normal interval may understate tail risk even if the conditional mean forecast is sensible. Prediction intervals should be distinguished from confidence intervals for the conditional mean. A confidence interval describes uncertainty about the estimated expected future value. A prediction interval must also include the new innovations that will arrive, so it is generally wider. Reporting the wrong interval can give decision-makers a seriously misleading impression of forecast precision. Estimated parameters introduce another layer of uncertainty. Many routine intervals condition on the fitted coefficients as though they were known. This approximation can be reasonable in a large sample and poor in a small or highly persistent sample. Simulation, bootstrap methods, or Bayesian predictive distributions can incorporate parameter uncertainty more explicitly. Forecasts must be generated honestly. A one-step rolling forecast updates the information set after each new observation, while a fixed origin multi-step forecast does not. Using residuals or parameter estimates computed with future observations leaks information and makes performance appear better than a genuine real-time exercise would allow. Choice of loss function should reflect the application. Mean squared error emphasizes large mistakes and aligns with conditional mean forecasts. Mean absolute error is less sensitive to extremes and aligns with a conditional median target. Directional or asymmetric losses may be relevant when under-prediction and over-prediction have different economic costs. Structural breaks are a major limitation. An ARMA model assumes stable dynamics over the estimation and forecast periods. A policy change, technological shift, or market crisis can alter the mean persistence or innovation variance. Expanding windows may then adapt too slowly, while short rolling windows sacrifice estimation precision. Non-stationarity also changes the long horizon story. A unit root process does not return to a fixed unconditional mean, and its forecast uncertainty can keep growing rather than plateau. Before applying stationary ARMA formulas, we must assess whether differencing deterministic trends or another non-stationary specification is more appropriate. The chapter example illustrates the forecast path and its uncertainty over multiple horizons. The point forecast returns toward the estimated mean, while the interval expands and eventually stabilizes under the stationary model. The exact path depends on the last observation, the last inferred innovation, and the estimated coefficients. Forecast errors should be examined by horizon, not pooled without thought. A model may perform well one step ahead, yet poorly at 12 steps, because small persistence errors compound through recursion. Benchmark comparisons are equally important. A complicated ARMA model should demonstrate an advantage over a historical mean, a simple autoregression, or another credible baseline. Here is how I would summarize forecasting. The model does the mechanical part. It tells us how today's information propagates forward and how future shocks pile up, but everything else is judgment. Diagnostics, rolling evaluation, alternative loss functions, and sensitivity checks are what tell us whether that story is still useful. So treat a narrow model-based interval for what it is. It is a statement inside the model, not certainty about what the future will actually do. We finish Univariate time series by asking why maximum likelihood estimators often work well in large samples. Two properties must be distinguished. Unbiasedness concerns the exact expected value at a given sample size. Consistency concerns whether the estimator converges to the true parameter as the amount of information grows. An estimator can be biased in every finite sample and still be consistent. The normal maximum likelihood variance estimator divides by sample size and is biased downward because the mean is estimated. Its bias shrinks to zero, so it converges to the true variance. Exact unbiasedness is therefore neither necessary nor sufficient for good large sample behavior. Let the score be the gradient of the log likelihood with respect to the parameter vector. At an interior maximum, the sample score is 0. At the true parameter, the expected score is also 0 under regularity conditions, because differentiating the integral of a density gives the derivative of 1. That 0 expected score result is not automatic, and it is worth saying why. We need to be allowed to swap the order of differentiating and integrating. The range of possible data should not shift around as the parameter changes, and the moments we rely on must actually exist. When any of these fails, say at a boundary in an unidentified model, or with an irregular density, the standard argument breaks, and the limiting distribution can change. The Hessian is the matrix of second derivatives of the log likelihood. Near a well-identified maximum, it describes curvature. Strong negative curvature means the likelihood falls quickly as parameters move away from the estimate, suggesting greater precision. A nearly flat direction signals weak information and potentially unstable estimates. Fisher information can be defined as the variance of the score at the true parameter. Under regularity conditions, it also equals the negative expected Hessian. This information equality links the random fluctuation of the first derivative to the average curvature of the objective, giving two routes to the same asymptotic variance. For independent observations, sample log likelihood divided by sample size converges to its population expectation under a law of large numbers. The population criterion is maximized at the true parameter when the model is correctly specified and identified. This creates the central consistency argument for maximum likelihood estimation. The Kullback-Leibler divergence clarifies identification. It measures the expected log density loss from using a candidate distribution instead of the true one. The divergence is non-negative and equals 0 only when the two distributions agree almost everywhere. Thus, the true parameter uniquely maximizes the expected log likelihood when distinct parameters generate distinct distributions. Consistency needs a little more than convergence at each fixed parameter value. We need that convergence to hold evenly across the whole parameter space at once. This is what a uniform law of large numbers gives us. Without it, The estimate could wander off into a region where the sample criterion has not yet settled down. The usual sufficient ingredients are compactness of the parameter space, continuity of the criterion, a dominating function that controls it, and identification, though the exact list depends on the model. After consistency comes asymptotic normality. Expand the score around the true parameter. The score at the true value satisfies a central limit theorem, while the average Hessian converges to its population limit. Solving the expansion shows that the estimation error, multiplied by the square root of sample size, approaches a normal distribution. Under correct specification and regularity, the limiting covariance matrix is the inverse Fisher information per observation. Consequently, the estimator's standard error shrinks at the square root of sample size rate. Doubling sample size does not halve a standard error. Approximately 4 times as many observations are needed for that improvement. The Kramer-Rao bound says that within a regular correctly specified model, no regular unbiased estimator can have smaller variance than the inverse information bound. Maximum likelihood estimators attain the bound asymptotically under standard conditions, which is the sense in which they are often described as asymptotically efficient. Scaling conventions can cause confusion. Some software reports the Hessian for the full sample, which grows with sample size. Other derivations use average log likelihood and information per observation. The inverse full sample information estimates the covariance of the estimator, while inverse per observation information must also be divided by sample size. The information equality offers a useful diagnostic under correct specification, but it can fail under misspecification. If a Gaussian likelihood is used for non-Gaussian innovations, the variance of the score and negative expected Hessian need not match. A sandwich covariance estimator combines both matrices and can provide valid quasi-likelihood inference under suitable conditions. Dependence changes the technical tools. In an ARMA model, log likelihood contributions are conditional rather than independent. Stationarity, ergodicity, moment conditions, invertibility, and suitable weak dependence support laws of large numbers and central limit theorems. Initial values must also become asymptotically negligible for conditional likelihood arguments. Parameters near a unit root or an invertibility boundary are not regular interior cases. Convergence can be slow, finite sample distributions can be skewed, and standard normal approximations may be inaccurate. The same warning applies when autoregressive and moving average roots nearly cancel, because the model becomes weakly identified. A simulation makes the asymptotic ideas visible. Draw independent normal samples with true mean 5, true standard deviation 2, and sample size 1000. For each sample, compute the maximum likelihood estimates of the mean and variance. Repeating this experiment 100,000 times produces empirical sampling distributions. The estimated means cluster around 5 and look approximately normal. The variance estimates cluster close to 4 with a small finite sample downward bias. Their dispersion matches the predicted square root rate. The simulation illustrates a theorem under favorable conditions, but it cannot prove that the same approximation is accurate for every model or sample. Estimated standard errors should be checked against how the estimator was constructed. Conditional likelihood, exact likelihood, robust quasi-likelihood, and bootstrap procedures can deliver different uncertainty estimates. Reporting a point estimate without its sampling framework hides important assumptions about distributions, dependence, initialization, and model correctness. The likelihood ratio, score, and Wold tests all lean on the same idea. Near the maximum, the log likelihood looks like a smooth upside-down bowl, roughly quadratic, and all three tests read off that same curvature. Under the usual regularity conditions, and when the null hypothesis is true, this makes them asymptotically equivalent. In a finite sample, they need not agree. A boundary restriction, weak identification, or poor curvature can make their usual chi-squared reference distributions unreliable. Consistency and asymptotic normality also describe different questions. Consistency says the estimator eventually concentrates near the target. Asymptotic normality describes the local shape and rate of that concentration. An estimator may be consistent with a non-standard limiting distribution, especially near a unit root at a boundary, or when a nuisance parameter is unidentified under the null. The most common mistake is to invoke consistency or asymptotic normality without naming the assumptions. A large time dimension does not repair non-identification, a structural break, a unit root treated as stationary, or an innovation distribution with inadequate moments. Large sample theory is conditional reasoning, not an automatic reward for collecting more dates. Across this chapter, the pieces now connect. Stationarity stabilizes distributions or moments. Ergodicity and mixing justify learning from one path. Wold's theorem explains innovations and linear filters. ARMA polynomials provide parsimonious dynamics. Likelihood estimates the parameters, and its large sample theory quantifies uncertainty. Our final practical rule is simple. Start from the economic and forecasting question. Choose a defensible dynamic specification, estimate it carefully, and inspect residuals and stability. Then use asymptotic inference as one calibrated approximation, supplemented by simulation or resampling when regularity is doubtful. Statistical theory guides judgment. It does not replace it.